Alright, now stretches and compressions, which are the harder of the shifts that I believe they're the harder of the shifts. But again, what you have to keep track of is one's happening to the x values and one's happening to the y values. Vertical is always the y values, right? Because the y-axis is the vertical axis. That's kind of how I remember it. Alright, so suppose I start with a function f of x, and then we multiply the function by some constant. Alright, so that's what we're doing here. We're multiplying by a constant. And so what you're literally doing is taking every y value and multiplying by the constant. X values are staying the same, and so you're multiplying by whatever that constant is. So if the constant is bigger than 1, right, not a fraction, it's bigger than 1, when you multiply it, it's a stretch. All the y values are multiplied by c, right? That's what's literally going on. X values stay the same, y values get multiplied by c. So if it's a fraction, meaning the c value is between 0 and 1, so it's like a half or a third or something along those lines, it's making it smaller, because of what you can think about it, if my c value is 1/2, right, if I take my y values and multiply by half, well, that's the same as taking y and dividing it by 2. And so all of the y values, in this case, are shrunk. They're divided by c, right, whatever that c is, and so they shrink by that fraction. Think about it as they shrink by the fraction 1 over c. Right, so if they're bigger than 1, they multiply and it's stretched, it gets bigger. So the graph actually gets thinner in that case because I'm stretching it out. When I multiply by a fraction, it's the same as dividing by that number. I compress it. Another way we could say this is a compression. And my graph shrinks. I'm shrinking by whatever fraction that is. And so we're going to look at an example of that case. And this time I'm going to use I did quadratics in these shifting cases. And so now I'm going to switch gears and look at the square root function. Alright, so this is the original function. Alright, f of x is the square root of x. And so I graphed 3 points on it. The 3 points that I graphed were 0, 0, 1, 1, and 2, 4. Right, those are the graphs that I have. And we're going to specifically look in at this point. We're going to see what happens here with that point 2, 4 when I manipulate it. Now I will talk about all of them, but that's the one we're sort of going to focus on because that's the easiest one to see when it stretches and compresses, shrinks. Alright, so there's the original graph. So f of x was originally the square root of x function. And so the first one's going to be a vertical stretch. So I'm going to stretch it by a factor of 2, which means I'm going to multiply it by 2. So my function gets multiplied by 2. And so my new function is 2 times the square root of x. And so that should stretch my square root of x function. Right, if I'm stretching it by a factor of 2, I'm going to multiply my function by 2. All of my y values get multiplied by 2, and if you look here, that's what's happening. 0 multiplied by 2 is still 0, right? If I plug 0 in, I still get 0 out. 1 multiplied by 2 will give me out 2, right? If I plug 1 in, a square root of 1 is 1. 1 times 2 is 2. And when I plug in 4, I get 4 out, right? Because my original value was 2, it got stretched to 4. And if you plug it in, you'll see that that is what happens, right? I plug 2 in, I plug 4 in. The square root of 4 is 2. 2 times 2 gives me out the 4. And so my new values, I still have 0, 0. Instead of 1, 1, I have 1, 2. And instead of 2, 4, I have 4, 4. Right? And so I did take 2 times all of my y values, right? If you look at that, all of my y values got multiplied by the 2, the factor of 2. And so that's what happens to the graph. So if you look at the graph, it's a vertical stretch, meaning I'm making it further away from the x-axis. I'm stretching it. I'm pulling on it and moving it in the upward fashion. And so it's moving in the vertical, right? A vertical, so it's moving, stretching it up or down by 4 units. So I went from my original graph was 0, 0, 1, 1, and 4, 2, right? That was the original graph, square root of x. And that original graph got pulled up by 2. Every single y value on this function got multiplied by 2, and it was a vertical stretch of 2. Alright, so that's what happens when we stretch it. Vertically stretch it. Alright, well, a vertical compression or shrinking it, compression, some books use the term compression, or this book typically use shrink. But compression and shrinking are the same thing. It's pushing it down, right? When you compress something, you push on it, right? And it shrinks. And so if I want to shrink by a factor of 1/2, that means all of my y values get multiplied by 1/2. And so my new function, my f of x, gets multiplied by 1/2. And so it's 1/2 times the square root of x. That's my new function. If I'm taking my original square root function and shrinking it by 1/2, so I'm making all of the y values get multiplied by 1/2. Or if you think about it, all the y values get divided by 2. Same way you can think about it. Y value gets divided by 2, and that's what happens when I plug them in. Every single one of the y values, my original graph, so the original, my square root of x was my original. The original points were 0, 0, 1, 1, 2, 4, right? That was the original 3 points. Keep shifting by my hand. Every single y value gets shrunk. So vertical is the y value. Y values get shrunk by 1/2 or divided by 1/2. And that's what's happening. 0 divided by 1/2 is still 0. 1 divided by 1/2 is 1/2. 4 divided by 1/2 is 1. And so I went from 0, 0 to still 0, 0. I went from 1, 1 to 1.5, right? So again, it shrunk by 1/2. And I went from 2, 4 to 4, 1. 2, 4. 4, 2. Sorry. 4, 2 to 4, 1. All of my y values got multiplied by 1/2 or divided by 2, whichever way you want to think about it. And so again, it compresses my graph. It smooshed it down towards the x-axis. The original graph went through the point 1, 1, 4, 2. And so the original graph was up here, and that was the original square root of x. And so by multiplying by 1/2, we pushed it down. We pushed the distance it was away from the x-axis by 1/2. That's what happens. That's why we say by a factor of 1/2. It gets smooshed down by that 1/2. If it was a third, it would get smushed down by a third. If it was a fifth, it would get smushed down by a fifth. Alright, so compression or shrink. So again, it's whenever it's vertical, it's always affecting the y value. Alright? So I'm going to do a couple, since vertical stretching and compressions are the harder cases. Compression is the same thing as shrinking. It's a term you can use either way, shrinking or compressions. You can always use the graphing calculator to check your answers if you check them in a standard window. Alright, I'm going to graph them by hand, but you have that, always have that ability. You can always use your graphing calculator to double check these. So the original function was actually the x squared function where I shifted it down 4 units, right? So my original was f of x equals x squared minus 4. And so it got shifted down 4 units. So it's at the end. Again, I'm going to graph a few 3 points. 1, 2, 3, 4. So it puts me here at -4, 1, -3, and -1, -3. Alright, those would be the original points when I shifted down. Alright, so there's my f of x function. Right, now I'm going to stretch that by 2, right? We're going to stretch by a factor of 2, because I'm multiplying it by 2. 2 times f of x, which gives me my function 2 times the x squared minus 4. And so it's actually going to make it skinnier. And so what we're literally doing is we're taking 2 and multiplying it by all the y values. So my original points were -1, -3, 1, -3, and 0, -4. Well, the new points, when I do this stretching, the x values stay the same, so it'll still be at -1, but instead of at -3, it'll be at -6. 0, -4, well, instead of being at 0, -4, it'll be at 0, -8. And instead of 1, -3, it'll be at 1, -6. And you can check it on your calculator. That is what happens when I do this vertical stretch. And I'm actually going to graph it on a completely different grid since it's sort of messy there. So 1, 2, 3, 4. I didn't give myself enough room. Try to graph it out a little better than that. Since I have to go down, I'm going to give myself more room in the negative direction. Alright, there's my x-axis, there's my y. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to shift down to 0, -8. So there's 0, -8. It's going to be at 1, -6. So 1, 2, 3, 4, 5, 6. And it's going to be down here at -1, -6. And so what has happened is it's stretched the graph. And if we go look at our graphing calculator, that's what's happening. It's stretched it. It's made it, it's pulled it and stretched it out. And so, actually my graphing calculator, I forgot, wasn't working, so I can't look at the graph. So you look at the graphing calculator. If you look at it, the original graph, which would have been here, 1, 2, 3, 4, would have been like this. And so that was the original graph, f of x. The green graph is the stretched graph, g of x. And so again, it stretched it out by 2 units. And how it does that is it multiplies every single y value gets multiplied by that number out front. Alright, let's do a compression. Same graph actually, but we're going to do a compression. Again, starting out with the same f of x, which is the x squared minus 4. So it's that function. 1, 2, 3, 4. So again, the 3 points that we're going to use are 1, -3, 0, -4, and -1, -3. This time, though, we're going to do a vertical shrinking by 1/3. And so our compression by 1/3. Multiplying my original function by 1/3, right? H of x is taking 1/3 and multiplying it by f of x. And so it's 1/3 times the entire function x squared minus 4, right? That was my original function. And so what we're literally doing is my x values stay the same, my y value gets multiplied by 1/3. Or again, think about it as all my y values get divided by 3. Right? Every single one of them is going to be divided by 3. And so my original y values were -1/3, +1/3, and so again, those are going to become, my -1 stays the same, but I take my -3 and divide by 3, and so I'm going to get the new point, -1, -1. 1, -3 is going to give me, divided by 3 is going to give me my new point 1, -1, so those are the new points. And then my vertex, which was at 0, -4, is at 0, -4/3. So at 0, at -1 1/3. Alright, and so it's going to smush it. If you look at it and you graph it, it does smush it down. Alright, so my new points, if I graph it with my new points, were at -1, 1, so here and here, and then at -4/3 would push me at 1 1/3, so somewhere about right there would be -4/3, and so it's a much fatter parabola. If I graph the original function with it, the original function would be here. So the original function's the blue case. That's f of x. And that's h of x. And so you'll see the compression, meaning we smush the graph closer to the x-axis. The distance between all of the points on my graph went down by 1/3. Right? It got smushed by 1/3. Its vertex was 4 units away. Now the vertex is only -4 1/3 away. Right? It got smushed by 1/3 of a unit. And every single point on this graph got compressed by that 1/3 of a unit. All of the y, and again, it smushes it. If you graphed it on your calculator, this is what should come out. The original graph is the skinnier one. The compressed one is the fatter one, because again, it's been smushed down, shrunk closer to our x-axis. Right? All of my y values get shrunk by 1/3. Alright, and that's vertical stretches and compressions. So vertical has to do with the y value.